Okay, hello everyone. I hope everyone can see my screen and can hear me clearly. If not, please let me know. Okay, so uh, last time we were covering the assembly language instructions for programming AVR microcontroller, and we had covered a couple of instructions. For example, LDS, which stands for load direct from data space. I'm not going to again explain the same things. I'm just trying to give you a quick recap so that we can continue with our today's lecture. The other instruction we covered was store direct to data space, or STS. Uh, then we had some couple of example for writing programs involving LDS and STS instructions. Uh, then we also had some example about add and okay. Mm, yeah, I'm just trying to figure out whether we covered these slides or not. I think we covered them, right? Can anyone confirm me if we covered these slides or not? Until this point, the current screen which you can see on my Zoom, did we cover the STS and LDI instructions, right? Anyone who thinks that we haven't covered them? Okay. I think we did, yes. Okay, okay, okay. So then I'm continuing with the next slide. So remember last time we talked about the division of the data memory space. So basically we said like the data memory space or address space is divided into different chunks, where the first chunk of the first 32 addresses are assigned to the general purpose registers R0 to R1. Then we have 64 four addresses for 64 special purpose register or special function registers. And in those versions of the chip where we have extended IO, that for them, for those special version, we have 160 next addresses for extended IO, and then remaining of the data spaces for the SRAM or static RAM, right? So now, in the previous slides, we have seen the instructions LDS, STS, load immediate, add, subtract, right? But now we are going to see another instruction which is in, and this instruction basically is specific for reading from the IO address space. So what does it mean that specific for reading from IO address space? It's mean that you can, when you use this instruction, then you must provide an address in the address range of IO address, which basically mean the address must be in this range from 0x00 to 005F, assuming there are no extended IO registers. Okay. So which means like if you use an address out of this range, then you will see an error. Okay. So for example, if we are saying in 0x3FR1, what does it mean? It means that read the data from the register or from the memory location which is addressed by this address 0x3F, read that data into the R1. Now, when we look into the mapping of the address spaces of the special purpose registers, we find out that 0x3F is basically address of the status register. We can confirm it from the previous slide here. So what was the address? 0x3F. Now, if you go to the previous slide and you look for 0x3F, where is 0x3F? Here you see that its address is 0x3F. So here in this column, the first column here, it gives the address in the IO address range of that particular register, special, for example, status register. And then this address basically, the second column, it gives the address of the same register in overall address range in the memory. Okay. So, but when you are using the in instruction, you must use the address of the registers in this column, IO address space, as it said here on the column header. Okay. So here what we are saying, we are saying that read the value from the memory location which is addressed by this particular address 0x3F, read that value from that memory location and put into R1. but this 0x3f is basically pointing to the status register. Okay. Similarly, when you say read the value from 0x3e address of the memory and put it in the R7 register. So again, since we are using in, so we must use an address in this particular range, within this range. And when you go back and look at the table again, you will find that this is the address of another special purpose register, which is used for serial communication. Okay. So we will cover these special purpose registers later on when we will, for example, we are talking, for example, about serial communication. But right now, it's enough for you to know that our focus is like in instruction. So it is enough for for you to know that if you are using this instruction, you need to specify the address within the IO address range. We have a complementary instruction out, so which actually performs exactly opposite of in instruction. So here what you are doing is you are saying like, okay, I want to output the data I want to like get data from a from a general purpose register and put it back in the special purpose register, right? So let me just clean this so that uh, the figure doesn't become confusing. Okay, so here again, just like all other instructions, this is our destination and this is the source. So what we are doing is like, for example, when you say 0 out 0x3f R12, so you are now saying that put the value of the R12 register into the memory location having an address of 0x3f. But when we look at that memory location, actually it is a pointer, or it is pointing to the special purpose, status register. So whatever value you have in R12, it will be stored in that memory location, which is for status register. Again, same thing here when you say out 0x3e R15. So you are saying, okay, put this the value of this register R15 in the memory location having an address of 0x3e, and which is basically the address of SPH, a register and used for the serial communication. Okay. Uh, but again, keep in mind, whenever we are using in or out instructions, we must use an address within this IO address space or address range. Okay. Any questions here? Okay. So basically using in and out instruction, you can read and write the IO space registers, special function registers. Okay. Another thing is like when you are writing assembly, your assembler is aware of the register names. So there is no requirement that you must use the address of the registers. For example, uh, again, let me erase these annotations. Okay. So for example, here we are again using the same out instruction, but we instead of like specifying the address of the SPH register, we can write the name of the register itself, and everything else stays the same. The effect of this instruction is exactly the same as if you specify the address of the register. But the advantage of specifying the name of the register is that it is more readable, one thing, and second, you don't need to remember the address. You don't need to like consult the table which I have shown in the previous slide. You don't need to go there and find the address of a particular register to which you want to read or write. So this is like more user friendly and more readable. Similarly, you can do the same thing with the in instruction as well. So instead of like specifying the address of the register, you can directly specify the name of the register itself. So these two things are equivalent. Here you can see whether you write the address of the register or you write the name, it will do the same thing. Okay, so let me again erase these annotations and then we can do our example. Okay, so example is to write a program that adds the content of the pin C IO register to the content of the pin D and stores the result in the location 0x90 of the SRAM. Okay. Remember this pin C and pin D, these are register, okay? These are registers, these are special purpose registers, special function registers, which basically mean that they are in the IO address space range. Okay. Now you need to write a program, and the job of the program is that it should add the content of the pin C register with the content of the pin D register and then store the result of the addition back in the memory at location of 0x90. Okay, now go ahead and start writing the program. You have 2 minutes to do that. And when you are done, let me know. In the meantime, uh, while you are doing the example, let me quickly check if someone is sending me an email from students, because sometimes students say they cannot access the Zoom meeting. No, okay, there are no issues. Again, I am just trying to clarify the example. Pin C and pin D, these are two registers these are two special function registers, so which basically mean that they fall in the IO address space range. So what your job is that you need to add the content of the pin C and pin D register together, and after the addition you need to write the result back in the static memory at address of 0x90. So write a program and let me know when you are done. Okay. Wait for some more students to finish their program. Do you need more time, or do you think that I should go ahead with the solution and show the program? I mean, if you are struggling and you think like you cannot do it, let me know, then I can explain it. But if you just need the time and you are able to do it, then I can wait a little more. Okay, want to see the solution. Okay, okay, good, good. Okay, then let's go with the solution. So remember, we said that pin C and pin D, these are just registers, special function registers. So you want to add their values together. So which basically mean you first need to read their values, right? So and you can read their values by using the in instruction. So you are actually saying, okay, now read the value from this register into the general purpose register R20, and from register pin D into general purpose register R21. And then you use the add instruction, which is you have seen earlier, to add the two values together. So now you have the result of addition in register R20. And then you can use the STS instruction, which is like store the value to the SRAM uh, by uh, by specifying the address. So now what will happen that the result of the addition will be saved in the memory at this particular address. Okay. Any questions? If you think you don't understand the example, let me know. Okay. Aaron, uh, is it clear to you or not, or you need more explanation on this? I understand now. Okay, good. Okay. So we in the previous slide we mentioned the status register, right? So what is that status register and why is it what is it used for, right? So let's have a look. So status register actually it is an 8-bit register in your AVR microcontroller, and each bit in the register has a special meaning or a special label. So let me first, like if you start from bit least significant bit, so you have carry bit, 0 bit, negative bit, overflow, sign, half carry, temporary, interrupt. Now these bits actually you cannot how to say manually set their values. uh or no, actually you can override the register, but what happens is that normally when you do some operations, for example if you do add operation, or if you do subtraction, or like and or any kind of arithmetic logical operation, so what happens that as a result of that operation, the values of these bits are changed. They may become 0 or 1, right? And then based on these bits, some other instructions perform their operation, right? So yeah, okay. So here I think the most important thing bits we are going to cover are carry flag, uh, our half carry flag, and zero flag. So let me explain first what is their functionality. So carry flag, so whenever let's say you do the addition, right? Addition of two 8-bit numbers. So whenever there is an carry out from the most significant bit position as a result of addition, then this bit will be set equal to 1. Or when you do the subtraction and when there is a borrow in the most significant bit position, then then this carry flag will be set equal to 1. Otherwise it will stay 0. Any questions? I mean, do you understand when carry flag is set or reset? Okay. Hmm. I'm sorry, could you explain again? I didn't understand. Okay. So yeah, I can I can explain definitely. So for that, I would need to go back to a note. Okay. So we have week 3, day 1, right? Okay, so let's say that you want to add uh, two numbers, and let's say both of them are 4-bit binary. Okay, I don't want to use 8-bit binary because then it will take time. So let's say I want to add uh, 1 0 0 1 and 1 1 0 0. So what will be the addition? Here you will have 1 0 1, and when you will add these two ones, so what will be the value? 2, but we cannot write 2 in binary. So what it will be? It will be the binary of 2 is 1 0, right? So we will write 0 here, and we will have a binary out which will be 1. This is carry out which will be 1, right? So if we have 4-bit numbers, then this fourth bit is the most significant bit, right? So if we have a carry going out of the most significant bit, then it's mean that we have it's mean that the carry flag in the status register will be set equal to 1, right? On the other hand, if I add number 0 0 1 0 0 1 0 1, if I add this number, so and again I'm saying my, let's say my register is 4 bit, so most significant bit is fourth bit on this one, right? This one. So I have 1 1 1 0. There is no carry out of the most significant bit, right? If there is no carry out, so C is equal to 0, right? Do you get it? Let me know if not. Okay, good. So another same is the case when you have subtraction. Now let's say I want to subtract, I want to do 2 minus 3, and for that I'm not using 2's complement. I'm just using signed numbers. So binary of the 2 is 4-bit binary of 2 is 0 1 0, and 4-bit binary of 3 is 0 0 and 1 1. Actually, I have another example which I don't need to, like, I can do it here. So I can just simply show you. Let's say we have like, this is this is 4-bit binary of 8-bit binary of 7, and this is 8-bit binary of 8. And what we are doing is 7 minus 8, and we are not doing 2's complement of 8, right? So when we subtract, so here we will get 1 1, here we will get 1 1 1. But when we reach at this point, we cannot subtract 1 from 0, right? So we need to get binary. We need to get borrow. We need to borrow the value, but we cannot borrow from here because this is also 0. We cannot borrow from here, from here, from here. So we borrow in from the most, in the most significant position, which is 2. But then we shift it, we transfer it. So when we keep transferring, we transfer the base of the system, which is 2. But the location from where we are transferring, the values reduced from 2 to 1. So here we get 1 1 1 1, and here we get 2. So 2 minus 1 1, and all other bits are 1, right? But the point here is that there is a borrow in the most significant position. So carry flag is set equal to 1 in this case. But if we subtract 8 minus 7, then there will be no borrow in the most significant bit position, and carry flag will be equal to 0. Okay, clear? Okay, I'm continuing, and okay, that helps. Okay, good. So here in this figure, basically what we are saying is like, uh, so this carry flag is set whenever there is a carry out or borrow in the most significant position. The 0 0 flag is set when you do some operation and the result of the operation is 0. For example, when you add two number and the result of the number and the result of the addition is 0, then this flag will be set equal to 1 in the status register. Okay, and it will be set automatically. You don't need to do anything. Like for example, if you you have in R1 you have 0, in R2 you also have 0, and when you say add R1 R2, the result of addition is 0, so this Z flag will be set equal to 1. Okay, whenever, like, and it doesn't depend only on add, it also, like, other instructions also affect the value of this flag. For example, decrement instruction, right? So when you will go to the appendix of the book, where they explain the instructions, they have listed that the set of the flags which are affected by each instruction. Okay, and the other so our flow is uh, uh, basically when your values, when you do addition and your when you, let's say you add two numbers and the result of the addition is greater than the 8-bit. For example, what is the maximum value you can store in a 8-bit in decimal form? It is 255. Now if you add let's say 255, and you add in register R1 you have 255, and in R2 you have value of 1, and you say okay, add R1 R2. Now there will be overflow because there is the result of addition is 256, which is not possible to hold in a 8-bit register. So then this uh, overflow flag will be set automatically. Okay, this value will be set, negative value will n will be set when the result of an operation in a register is negative in its value. And half carry or sign, they are not important at this point, but when we need, I will come back to this register again when we need them in some instruction. Okay, so now let's go to an example. Show the status of carry flag, uh, half carry, and Z flag. I haven't explained the half carry. Let me also explain first the half carry. Again, I can go back to the OneNote. So half carry is when you have, uh, let's say you are adding again, let's say you are adding two numbers, and again I'm taking an example of 2-bit numbers. Okay, so for example, give me uh, for example 0 0 1 0 and 0 0 1 1. When you add these two numbers, let's say my register is 4-bit. If my register is 4-bit, what is the half of the half size of the register? 2-bit, right? So if I add 0 and 1 1, if I add 1 1, it will be 0, and then there will be a carry into the next position, because the result of one adding 1 and 1 is 2. So here I will have carry. So 1 and 0. So when I have a carry from the half position, or a half size of the register, then your H flag will be set equal to 1. I'm just giving the example using 4-bit, but actually we have a 8-bit, which basically mean that when there is a carry out from the bit position B3 to B4, then your carry will be set, your half flag will be set equal to 1. But if there is no carry out from the bit position 3 into bit position 4, then H flag will be set equal to 0. Okay, clear? If not, let me know. Okay. So now you know how carry flag, your half carry flag, and how Z flags are set. Now let's say that we are going to do the addition, and we need to find the values of these flags. So show the status of C, H, and Z flags after the addition of 0x38 and 0x2f in the following instruction. So basically what you are doing is that you are loading the value of 0x38 in R16, you are loading the value of 0x2f into R17, and then you are adding these two numbers. Now do on your notebook, do the addition of these two numbers and based on the addition result, tell me the value which we will have for C, H, and Z flag. You have 2 minutes to do that. Sorry, I'm having cough today. Sorry. Let me know when you are done. Okay. Okay, someone. Okay, I mean, up to you, but I would encourage you to share your solution. I mean, if you are done. Mm. Yeah, but up to you. I don't want to like force you. I bound you, but I mean, if you can, it will be good. Uh, Yeah, but we need to know the values of C, H, and Z flag. C, H, and Z flag. Yeah. Okay. Okay. Uh, I think I can give 1 more minute for other students to complete because I don't want that I can see like there are only 3 4 students who are all the time responding. So I also want other students to participate. So if you need more time, please let me know. Okay. You are confused? Okay, let me know what's the confusion. A student said that he or she is confused. Please let me know what's the issue. You can unmute yourself and you can talk.
I'm confused about the flags. I'm not understanding that.
Uh, about the flags, like what is their significance? How they are set or reset? Or like, mm, are you confused about like when we set their values to 0 and 1?
Yeah, I'm confused how they play a part in all of this.
Okay, so there are two parts. First we need to know like uh, first thing is like there are some instructions which actually check these flags before executing. Like for example, we say in branch instruction, which I guess you will be using in lab 3. So branch instruction are actually also we have used the branch if equal instruction in one of the previous lab in lab 1 or lab 2, I guess, right? So, what does this branch if equal instruction do? It actually looks at the Z flag. If the Z flag is 0, then it goes to the it takes the jump. Otherwise, it doesn't. Again, maybe it looks to you it's look like that. Maybe it looks like I'm talking in the doesn't I'm not making any sense. Then let me go back again to OneNote. So I can give an example. Uh, yeah. Let's say we are writing a program, okay, and we are writing an assembly program, right? I'm not writing exact assembly instructions, but let's say we have some instructions here and we have a label here, right? And then we want to actually what we want to do is that we want to do these instructions multiple times. So we want to have a loop, right? So how can we do that? For example, what I can do is that I can say, okay, in register R16, put the value of, let's say I want to do this loop 10 time. Put the value of 10, right? Now in R16, I have 10. And here I have some couple of instructions which I want to execute 10 times. And then here I can say, okay, decrement. Actually, we have used exactly this thing in previous lab. So I say okay, decrement R16, right? And after that I say uh branch if 0, branch if not equal, right? Uh so I think it was, let me erase this one. So uh let's say I'm saying branch if if 0. I'm here just making this disclaimer. I'm not exactly sure if our AVR microcontroller has this instruction, but let's assume there is an instruction, okay? I'm pretty sure if they don't have branch if 0, they have an equivalent of it. Maybe the name is different, but there is an instruction which does the exactly same job, which I'm going to explain. So then I say branch if 0. So what does this instruction do? I mean, what is the syntax? This instruction will actually look at the status register on in the Z flag of the status register. And if the Z flag is 1, uh, uh, if the Z flag is uh, sorry, again I need to erase this thing again. Branch if not zero. Okay, so this is branch if not zero. So this instruction will basically look at the Z flag of the status register, and if this value is equal to 1, then it will actually and here I need to give the label whatever label it is. So if the value of the Z flag is 1, it's mean that the result is 0, right? So, but if the value of Z flag is 0, it's mean that the result of this operation was not 0, right? So again, 1 mean result was 0. It's difficult bit to write here. Result is 0 and result not 0. Okay, so now when we have this decrement, let's say I have the value of 10 in 16, right? So what will happen when I execute these instructions? After that, the value of R16 will be decremented and it will become 9, right? So it will say branch if not 0. So it's not 0. So then this instruction will basically, what this instruction is doing. So after decrement, since the value of the operation is not 0, so then Z flag will be set equal to 0, right? So this instruction will now test the Z flag, and it will say, okay, the Z flag is telling me that the result of the operation is not 0, it is something other than 0. So then I'm branching to label. So it will again go to label, again perform these instructions, and then when it reaches here, it will decrement again. It will become 8. Now, since the operation value of result of operation is 8, which is not 0, so then Z will not be set equal to 1, it will stay 0. Branch not 0 will again look at the Z flag, and it will see, okay, it is not equal to 1. So basically, which means the result is not 0. So I will go back to the label, right? So who is setting this Z flag? This instruction is actually setting the flag, and who is testing? This instruction is testing or checking the value of the flag. So this is how these flags are used in the programming. Okay, and there are also other instructions which actually use these flags, but we are not going to cover them at this point. We want to just understand how the value of these flags are set. Okay, do you understand now?
Yes.
Okay, someone says the lab use branch not equal. So E stands for not equal, branch if not equal. Okay. Now let me go back to the slides. Okay. Questions are good in one way, but they are bad in another way because they then slow me down. Okay. It doesn't mean I'm asking you to not ask the questions. You can. Okay. So what was our, where were we? Go back. We did these slides, right? Why I'm losing track of the, yeah, we were done this one. Yeah. Yeah. Okay, so this is the result of this example. Everyone, is there anyone who thinks that the result should be different than C is equal to 0, H is equal to 1, and Z is equal to 0? Is there anyone who thinks that the result should not be this one? If you think that this is not the correct answer, let me know. I can explain. Here, actually, they have done this addition, right? So when you will do the addition, there will be a carry from bit position 3 into bit position 4. There will be no carry out from the most significant bit position, and the result is not 0, right? So since result is not 0, then Z flag is set equal to 0. Since we have a carry over from the bit position 3 in the bit position 4, that's why we have half carry flag set equal to 1. And since there is no carry out of the most significant bit position, that's why carry flag is equal to 0. Okay. Okay, show the status of C, H, and Z. Again, the same example with different values. So please do the addition of 0x9C and 0x64 and tell me the result, the values for C, H, and Z. After this addition, what will be the values of C, H, and Z flags? You have 1 minute. We need to be a bit quick because I want to also complete the slides. Please do the example. When you are done, let me know. Okay. Yeah. Okay. Good. Good. I'm gonna. Okay. Yeah. Z. Okay. I will explain. Okay. Let's wait for one more student to share the solution and then I can explain it. Okay. Okay. Good. Okay. So let's have a look. Some students said that Z will be equal to 0, which is not true. Why? Let me explain. So here when we do the addition, so the result of the addition is equal to 0, right? 8-bit result, right? Because we have 8-bit registers, we cannot count the ninth bit, right? Also there is an carry from bit position 3 into bit position 4, and there is a carry out from the most significant bit position. So if there is a carry from most significant bit position, carry flag is set. If there is a carry from bit position 3 to bit position 4, then half carry uh, flag is set. And if the result of the operation, whatever operation we are performing, is 0, then the Z flag is equal to set equal to 1. Okay. Now, if you still have confusion, let me know. Is this also overflow? Uh, yeah, this is also overflow. I will explain when we will have example, then it will become clear that how overflow flag is set, but that's, yes, it will also be treated as overflow. Okay, this example, I am not going to ask you guys to complete it. I can simply share the solution. So here we have the number uh, 0x a5 and 0x23, and we are going to do the subtraction. So we are going to subtraction of 0x23 from 0x a5, and then we need to look at the values of C, H, and Z flag, how whether they are set or not, set to 1 or set to 0, right? So basically one thing we need to know is that this is not like only addition instruction impacts the values of these flag. There are also other instructions, file number, subtract instruction, R, and R, exclusive R, and so on. So you can go, as I said earlier, at the appendix of the book, and there they explain for each instruction whether it affects a given flag or not. Okay. So here So this is like we first convert our A5 to the binary, then we are converting our second number 23 to the binary. Remember, we are be careful that we are not converting it to the 2's complement form. We are simply converting it to the signed form, and then we are doing the subtraction. Now, if you do the subtraction, so here you will get 0, here you will get 1. Why? Because there will be a carry. You cannot subtract 1 from 0, so you will get a carry. And then here you will have 0 because you will be left only 1. Remember, just like in decimal system, when you do borrow, you borrow the base of the system, which is like 10. In binary system, when you are doing subtraction, you borrow the base of the binary system, which is 2, right? So here you borrowed 2. When you borrow 2, 2 minus 1 is 1. But then if you borrow 2, so this one will be reduced, right, by 1. So if it is reduced by 1, it will become 0. 0 minus 0 is 0. 0 minus 0 is 0. 0 minus 0 is again here 0. And here 1 minus 1 is 0. 0, 0. 0 minus 0 and 1 minus 0 is 1. Okay, so it's straightforward, right? So carry flag is 0. Why? Because there is no borrow in the most significant bit position, right? And z flag is equal to 0 because the result of the operation is not 0, right? So it will be equal to 0. And half carry flag will be also 0. Why? Because we had no borrow from the bit position 4 into bit position 3. Okay. Any questions? Okay. Uh, we have another example. Show the status of the CH and Z flag after the subtraction of 0x73 from 0x52 in the following instruction. Again, let me walk you through the example, and if you don't understand, then you can inform me. Okay. So first you convert the numbers into the binary. So this is the binary of the both numbers 0x52 and 0x73. Again, the 73 number we are doing the subtraction, but here for the purpose of setting finding the values of the flags, we don't convert it to the 2's complement. We keep it in the signed form and then we do the subtraction, right? So here we cannot subtract from 1 from 0, right? So we do the borrow. So when we do the borrow, we get 2, 2 minus 1, 1. But here this is reduced, so it becomes 0. So we cannot subtract 1 from 0. So we get the borrow. We cannot borrow from this 0. We cannot also borrow from here. We can borrow from here. So when we borrow from here, we get 2. And then we like transfer it to the next position. So here we'll get 2. 2 minus 1 will be 1. Here will be left by 1 at this position. 1, 1 minus 0, 1. Here will be left. We will have 1. 1 minus 0 is 1. And then here we are left with 0 at this bit position 4. So we do borrow again. We cannot borrow from bit position 5. We borrow from bit position 6, right? So then we do the subtraction. So 2 minus 1 is 1. So here 1 minus 1 is 0. 1 minus, so here then we are left with 0 because when we borrow the number, the value of the bit is reduced by 1, right? So we cannot subtract 0 from 1. So we need to do borrow again. So we cannot borrow from bit position the 7 because itself it is 0. So we borrow from outside, like from bit position 8, for example, right? So when we borrow 2 here, when we shift it at the next position, so it becomes 2 minus 1, 1. And here we are left with 1. We borrowed 2, but then we transfer it, so we are left with 1. So 1 minus 0 is 1, right? So if we look at the how can we set the values of the flag, what should be the value of the flag? So C will be equal to 1. Why? Because there is a borrow in the most significant bit position. Z is equal to 0. Why? Because the result of the subtraction is non-zero, right? And H is equal to 1 because there is a borrow in from bit position 4 into bit position 3. Okay. Any questions? If you don't understand something, please let me know. Okay. No comments mean everyone understands everything. Okay. Uh, okay. So again, show the status of C, H, and Z flag after the subtraction of 0x9C from 0x9C in the following instruction. It is straightforward. Why? Because Both are same numbers, right? So when you will do the subtraction, the overall result will be 0. You are not borrowing anything from bit position 4 into bit position 3. You are not borrowing anything from bit position 8 into bit position 7. So carry flag will be equal to 0. Half carry will be also equal to 0 because we are not borrowing anything in both positions, and z flag will be equal to 1 because our result is 0. Okay, so remember z flag is 1 when result value of result is 0, and z flag is 0 when value of result is non-zero. Okay, any questions? Okay, so remember previously I explained that this instruction, for example, uh, uh, sorry, not this instruction, these flags like z flag, c flag, or h flag, they are used in many branch instructions. So here is a set of the branch instruction which uses some of these flags. We are not going to discuss them right now, but like here it just tells you that why it is important or why even these flags are needed. Because for example, we need this flag to do the branch instructions or to like jump in our programs, because remember, right, when we are writing the higher level language programs, we check the conditions, and if the condition is true or false, based on the value of that, whether the result is true or false, we do different things. So we want to do the same thing in assembly, and how we do that assembly? By using branch instructions. And what does the branch instruction do? How they do the branching or jumping? By looking at the value of the flags, and if and depending upon the value of the flag, you go to one of the two possible destinations, like either go to location 1 or go to the location 2. Okay, so for example, this instruction branch, if same or high, actually it checks the value of the C flag. So if the value of the C flag is 0, it's mean that that the values which we are comparing, they are actually either they are one, the first value is either same as the second value, or it is higher than the second value. And how it knows is that if c is equal to 0, actually we are going to use this branch instruction in lab 3. There I will go and explain it in more detail. But for other instructions, other branch instructions other than brsh, we will have separate lecture. We will go through them, and then you will understand how they work. But the main point here is that they basically check the flags, and based on the value of the flag, they branch to location 1 or location 2. Okay, so this is the same example. Okay, so we are at least done with this set of slides. Now let's go to the next set of slides, which is our today's set of slide. Let's see how much we can cover. Okay, so we are continuing basically with our assembly language programming. We will continue discussing some more assembly instructions or some directives also. So what is the first, before explaining these individual directives, let me explain what is the difference between directives uh, and your instructions. So instructions, when we are executing the instructions, we are actually telling the microcontroller hardware to do some operation. For example, when you say add, you are telling the ALU of the microcontroller to add two numbers. Similarly, when you say AND, you are telling the hardware of your microcontroller to do AND operation between two input numbers, right? But directives, they are also instructions, but not for your hardware. They are basically for your assembler. So in our case, we are using Arduino IDE, which has an assembler. So we are telling the Arduino IDE something by specifying the directives. What we are telling, it depends upon the directive we are going to use, right? So for example, uh, equate dot equ. So let's first have a look at its syntax, and then it's what is the meaning or semantics of this directive. So when we say equate name value, so basically what we are saying is that in our program, wherever we use this name, let me use the concrete example to explain it. Okay, so for example, if you say equate count 0x25, so now you are saying, you are telling your program, your assembler basically, that in my assembly program, wherever I write count, replace it with the immediate value of 0x25, right? So now when you will write load immediate R21 count, and you'll write another instruction load immediate R22 count plus 3. So what will happen? Your assembler will replace count with its value, which you have already equated to 25 in hexadecimal. So it will basically become that you are saying load immediate value of 0x25 into R21, and here you are saying load immediate value of 0x28 into register R22. But the thing is, like, once you have about the one thing about this directive is that once you have declared this directive and you have set a name for a particular value, you later on you cannot change it in your program, right? What does it mean? It will become clear when we'll discuss the next directive, which is set. Okay, so it is actually same. It has the same functionality as the equate directive, with the difference that we can change it in our program. Let me explain using an example again. This time we are using set directive to set the value of count to 0x25, and then we have these two instructions are same. So we are saying, okay, put the value of 25 into R21 register, put the value of 28 in R22 register. But after that we are saying again dot set count 0x19. So we are saying now reset this count or this name to the value of 0x19. And after this, if we say now load immediate R21 count, so now 0x19 will be loaded into R21. But we cannot do this with the equate. So if I write here, for example, dot equate, then my assembler will give me an error. I don't want to write here equate because it is hard for me to write on the slides. But if I, for example, if I use the equate directive to change the value of the name count to 0x19, you can't do that. Assembler will give an error. Okay. Any questions? Okay. Then there are two other directives, dot data and dot text. So dot data directive, we have actually used it in our previous assembly programs in the labs. So here we are saying that actually before explaining this, let me explain to you. We know that our memory is divided into like code memory, and in our or maybe can I undo it? No. Just give me 1 minute. So we know that we have code memory and we have data memory or SRAM, right? So I'm writing it as CM code memory and data memory or SRAM as DM, right? So so when you say dot data subsection, so actually you are saying that you are telling your assembler, you are giving the directive to your assembler to divide the data memory into sections, right? And then each one is named as is given is each one of them is called a subsection, right? So what you are saying is that assemble the following statements onto the end of the data subsection numbered subsection. Let me give you a concrete example. Do they have here? No. So for example, uh, if you say dot data. So if you say only dot data, but you don't say subsection, so what you are saying is that whatever I'm going to write here after data, after dot data, all of that, put it in the data memory, not in the code memory, right? But if you say, okay, data subsection 1, S1, so what will happen, right? It will name the first section as S1 and will start putting the data here, right? And let's say after that, I say dot data. Sorry for this bad writing, but if I go to the notepad, it takes time. And now if I'd say dot data s2 and after that I put some other instructions, so what does it mean? It means that whatever I'm writing here, put it in the also still in the data memory, but in the subsection 2. Okay, so this is what is meaning of the dot data subsection directive. Okay, any questions? No. Okay. Task dot text subsection, actually it has the same similar meaning as dot data subsection, but only for the program memory. This time what we are saying is that whatever I'm going to write here under dot text, let's say I am not using this subsection thing. I'm only writing dot text, and after that I am putting some instruction. So what it means is that whatever is written after dot data, put it in the code memory. So this is our code memory. Okay. But if I say dot text subsection, it basically means that okay, whatever, like for example, if I write dot text S1, so whatever I'm going to write here, put it in the section S1. This is S1. And if after that, if I say dot text S2, then it's mean that whatever instruction I will put in my program, let's say I'm saying S2, all of these instructions will go to the subsection 2 in the code memory. Okay, so this is what the meaning of the dot text directive. Any questions? No? Okay, now we have other two more directives, .com and .global. So .com actually stands for common. Okay, so com is for common. .common symbol length. So this is your syntax of the directive. So here you give the symbol, so and then the length. So here basically you use this directive to allocate the space. And for example, if I say, okay, go back to the one note. Okay. So, for example, if I write dot com symbol like for example x1 and then 1. So what does it mean? It means that in the data memory, actually make a variable and give it of size 1 byte, and give it the name of x1. Okay. And so, but what is the also the meaning of .com? It's mean that make it a common variable for all the code in the same file. For all the code in the same file. What does it mean? Let me go back here. Uh, are you guys familiar with with the higher level language, for example, C or C++? So in those language, we have a notion of global variable. What is a global variable? If you define a global variable in higher level language, so it becomes visible to all the functions which you have defined in the same program, in the same file, not same program, in the same file. So this is, we can do exactly the same thing in the assembly of the AVR microcontroller by using the .com directive, which basically we are saying that okay, make it visible to all the code in the same file, right? Any questions here about this .com directive? No? Okay. Now, we said that this .com directive makes the variable which you have declared in the memory, for example, x1, visible to all the code in the same file where you are actually writing this .com directive. But let's say if you have two different files in your program, in your sketch in Arduino, and you want to make this variable visible not only to the code in the same file where you are declaring it, but also to the other files in your project or in your sketch. So for that, you need to use the .global directive of the assembler. So how you use it? By putting .global and name of that symbol which you want to make visible to the code also in the other files in your project. So actually it is same as extern in high level languages like C or C++. Okay. So if defined in the current file, it makes symbol visible to the other files. Okay. Otherwise, symbol takes an attribute from a symbol of the same name from another file. So basically what you need to do is that whenever you need to expose a symbol which is defined in one file to the code in other files, you must put .global directive before it. Okay. Any questions? Please let me know if you don't understand the meaning of these directives because I know they are a little bit tricky. Okay, so here we have an example. So let's say we have this assembly file and we want to define some global data, right? So let's say we want to define the global values value val1 and val2, right? So dot data is actually I'm telling the assembler that whatever I'm going to write after this directive, declare it or put it in the, this is basically I'm saying this is for the data memory. Okay, and then I'm saying, so what will happen, let me do here what will happen now when you will say dot com val11, so actually 1 byte of memory will be reserved. It will be given the name of val1. I'm writing just v1 for that, and it will not be initialized. So this one is basically size of the memory allocation, right? But if I don't, let's say I don't use this global, this directive, next line, then what will happen? I can still use val1 in this file, right? I can still use it here, but I will not be able to use or access this variable in another file of my project, right? Which means that it will not be visible in the other file. That's why if I want to make it visible, I need to add this dot global val1. Now the next directive actually is saying, okay, allocate another memory of size 1 byte and give it the name of val2. I'm writing only v2. And then I'm saying I also want to make it visible to the code in other files in my project. Okay. Now here this directive is basically saying that whatever I'm going to write after this line, after this directive, this is for the code memory, not for the data memory. So here I have code memory now. So now this instruction, and now what is meaning of this dot global compute? So it's mean that make this symbol visible to the other files in my project as well, so that I can use them. Okay. So now this first instruction, it will go here in the code memory, and load immediate will also go in the here. All the instructions will go into the code memory. So in code memory, I will have these 5 instructions. Okay. Now let's have a look at how we can use uh, these variables. Remember, we have exposed that we said we want to expose them to the other files in our project by using these dot global directives, right? Now let's see how we can use them in the other file. Let's say we have another file which is of type C file. So this is assembly file here in our project, and we have the C file, or in Arduino it is .ino, but it uses the syntax similar to C. So first we need to tell the assembler that I am going to use a symbol val1 which is of size 1 byte, but it is not defined in this C file or .ini file. It is external to this file. It is defined somewhere in another file in the same project. So then assembler can go and look in the other files for this variable val1. Same thing we are doing for the variable val2. And then we are also telling the assembler that we are going to call or use a function compute, but that function is not defined in this file. It is also external to this file. Go look for it in another file in the same project. So it can go to this assembly file and find that, okay, yeah, we have it here. Okay. But then we also need to make it visible in the assembly file. Otherwise, if we, for example, if we don't use this dot global and this global, and we use only these external keywords here, we will not be able to access them. Okay. Now here we have, actually this is the same code which we have seen in our lab 2. So here we are running this, we are writing this function read to digital. So now in this function, we can use this val variable which we have defined in the assembly file. Oh, no, no, this is not that value variable. Those are val1 and val2. We are defining our new variables by type, int and val. Sorry, val of type int and inch of type byte. So then we are saying, okay, enter a 2-digit value. Then we are reading that value, and we are doing the math. and then we are actually returning some value. I don't want to go through this code because that is not the focus. So I just want to focus on how we are going to use those val1, val2 and compute, right? So then in the void setup, so what we are doing is we are saying we are calling this function which actually reads two-digit value, and then we are putting that value which is returned by the function. Remember, it is returning a byte type value. So we are putting it in the val1, and this is the C code. And how we why we can access it here? Let me check the time. We have 4 minutes. So why we can use it? Because we already we have already specified to the assembler that val1 and val2 are defined somewhere in another file in the project. Go look for it. That's why we can use it here. Same is the case for val2, right? And we can make the call to this function compute because we have told the assembler that this is an external function which is defined here in our assembly code. Okay, so that is the job of the directives, dot global dot common. Okay, there is a question. What do you have? Why do you have to put C uh, after extern? My guess is not a guaranteed answer, but my guess is that we are specifying that this is external for a C language program. So like we are saying that this is C written in C language. So we are just specifying that. Again, next time you can ask me again. I will try to like come back with a confirm answer. Any questions? Okay. We are left with 2 minutes. Should I use them or not? Okay. I will not go through this slide, but let me just set up the how to say the context for this slide. So remember we said that we have 32 general purpose register in our AVR from R0 to R31. So yes, we can use them to hold any values what we want to put, like anything we can put in those registers. However, there are some conventions which are typically used when putting values in these registers, and it's always better to follow those conventions because then it gives our code a little bit level of portability. Like for example, if you are writing a program and you are following those conventions, and I'm also writing a different program and I'm following those conventions, then it will be easy for you to understand my code. And also if I want to get your code and run in my machine, so it will be easier for me to understand how it is working, because we agree on conventions like how to use R0 register or R1 register. Though the default is that you can put any value in R0 register, R1 register, other registers, but then again there are some conventions which are better to be followed. Okay, we will talk about them in the next lecture. Any questions? Okay, there is something which I just want to mention regarding Lab 3. So Lab 3 was supposed to be released in last Thursday, but I didn't release it, and it is due on the next Thursday, which basically mean not Thursday of this week, but the next week, right? So I will not move the deadline. You are supposed to still submit to the deadline, which is the will be the Thursday of the next week. But if you think that if you think that you are not able to complete it by Thursday and you need some extension, let me know and I will like extend it. But I will encourage you highly to submit it by the next Thursday, because otherwise it will start overlapping with the next lab 4, and then you will be like, your work will start piling and you will be stressed. So it's better that you finish it by next Thursday. Okay, Thursday of the next week. Any questions? No? Okay, then let's stop here and we can